Okay, in part C, we're going to show that the second derivative of this function gives us this result, and then we're going to use that to explain why the approximation that we get applying the trapezoidal rule will exceed. Exceed means is bigger than the exact value. Now let's think about what we did in example 1. When we had a function that was concave up and the second derivative was greater than 0, we know that the area that the trapezoidal rule would provide, which is this whole region in here, would be bigger than the area under the curve. So that would be exceeding it. Here, if the function was concave down and we were looking at applying the trapezoidal rule, in this scenario here, we can see that the trapezoidal rule would give us a result that is underestimating. It's less than the area under a curve. So if we're looking here at when it's going to exceed the exact value, then obviously we're looking at where the second derivative must be greater than 0, because that's the scenario for which our trapezoidal rule will give us an overestimate compared to the area under a curve. So let's have a look at, if we start with this function y equals 6 on x, another way we could write that using our knowledge of negative indices, we could rewrite that as 6x to the power of negative 1. Now if we differentiate and find y dash, we bring 1 down to the front, so this becomes negative 6x, and we're going to take 1 off the indices, so this becomes negative 2. Now we want to find the second derivative, so we'll go through that process again. So we'll bring the negative 2 to the front, so it's negative 2 times negative 6x to the power of, and we're going to subtract 1, so it becomes to the power of negative 3. So multiplying this negative 2 by negative 6, we end up with positive 12x to the power of negative 3, as was required. Now we know another way we can write this is 12 over x cubed. Now let's think about where we're finding the area under the curve. Remember our table of values from x equals 1 through to x equals 5. Now if we substitute in either 1 or 2 or 3 or 4 or 5 into this function here for our second derivative, we know we're going to end up with a positive value for our second derivative every time. So in other words, the second derivative is going to be greater than 0 for all those values of x in between 1 and 5. So if our second derivative is always going to be greater than 0, that's this scenario here, and therefore our trapezoidal rule will exceed the exact answer that we would get if we were to apply methods of integration.